everyone. Welcome to the 15th talk of the seminar. Today, our guest speaker is Professor Suman Jana from Columbia University. Suman, if you are familiar with, like in the audience, if you are familiar with the work on verification in neural networks, then you very likely have come across some of his foundational work in this field. I think, as he has conveyed, his talk today will be on neural network verification using the efficient branch and bound methods. A very quick introduction about our speaker. Suman is an associate professor in the Department of Computer Science and Data Science Institute at Columbia. His primary research interest is at the intersection of computer security and machine learning. His research has received 6 Best Paper Awards. That's a that's a lot, actually. CACM Research Highlight, a Google Faculty Fellowship, a JP Morgan Chase Faculty Research Award, an NSF Career Award, and an ARO Young Investigator Award. So yeah, on that note, Suman, the virtual stage is all yours.
Thank you. Thanks, Vikash. Thanks for the introduction. And thanks again for having me at this seminar. It's my pleasure. And let me kind of share the screen to make sure that you guys all can share. Can you see my screen?
Yes, we can.
Is it all good? All right. Yeah. Thank you. So yeah, so as Vikash said in his very generous introduction, I work at the intersection of security and machine learning. A lot of my work kind of involves robustness of machine learning models, and also the other side, where using machine learning models for different security tasks like program analysis, more specifically bug finding, automated bug finding. But today's talk is going to focus on the other side, which is, talking about robustness of machine learning. And, robustness of machine learning has very different aspects, as I'm sure you have seen in this seminar, several different aspects. Mine is, one small piece in that big, plethora or a big set of techniques that have been used. We are going to talk about verification, and it will see in a second what is meant by neural network verification. But that's the flavor of robustness we're going to talk about. And branch and bound is a specific technique that we use. So that's the idea. And I'm going to describe joint work with several different folks from CMU, Northeastern, UCLA. So this is a big collaborative project. I want to thank all my collaborators, and I'll just summarize, the overall work we have been doing for last couple of years as part of this group, right? Okay. So let's begin. So the overall idea, as I said, we're going to talk about where verification fits in terms of reliable ML, and what is the formulation, what are the challenges, and then how to build state-of-the-art verifiers. Okay, so, as part of this seminar series, I'm sure you don't need any more motivation to talk about the importance of robustness of machine learning, especially in security and safety sensitive tasks like autonomous driving, medical diagnosis, and whatnot. So I'm not gonna overemphasize the point, but I'm sure all of you have seen these pictures, essentially talking about minor perturbations in input causing large mistakes in output. And these are traditionally known as adversarial inputs, right? So I'm sure, given the focus of the seminar, all of you have seen these kind of pictures, but the point to emphasize again is the seriousness of these mistakes, right? They can cause a very serious implications, right? So you want to avoid them as much as possible. Right, and so this, let's take a bit closer look. I'm sure, again, this is all very well known to you, you all, but I'm just gonna very briefly summarize adversarial examples. Essentially, you have this, input, certain inputs. You add very small targeted perturbation to that input. In this case, the picture of a cat, and the picture doesn't change after the perturbation, but the result is gonna, the output of the model is gonna change a lot, right? So that, in this case, changes the classification from cat to dog, let's say, right? So that's kind of the issue we are talking about. And this kind of adversarial examples it has been shown widely that they are fairly easy to find using standard gradient descent based optimization techniques, right? I'm sure you're again familiar with all the different attack techniques like projected gradient descents, the PGD, or fast gradient sign method, FGSM, and they're like a bunch of different attack techniques. But all of them at the end of the day are solving this particular optimization technique, as you can see here. Optimization problem, as you can see here, if you can see my cursor, is just trying to make the prediction change as much as possible. Okay, FX in this case is just a prediction, right? So this is great, but this is great in the sense, this is great from an attacker's perspective, but this is not great from a defender's perspective, right? Because you want to be able to train and deploy models that hopefully should be robust to this sort of attacks, right? So there are, again, many different ways of trying to make models robust. Our specific way for this line of work is essentially what is called neural network verification, right? So what does that mean? Well, I'll describe it in a second. But verification, if done right, can provide quite strong guarantees, right? That's the idea. And let's take a closer look at about what I mean by verification, right? Okay. So in this context, we take a neural network as input. For this problem, we're going to define it that way. There are different variants, but imagine the neural network has been trained. You have done whatever you want to do with the neural network. The weights are fixed. At this point, the verifier takes the neural network as input. And then it takes something called the safety property or security property as input. This basically specifies the desired behavior of the neural network's output over a given input region. Okay, and note that this is fairly generic, right? When I say input region, how do I define input region is also another question, right? Like, because I want to be able to say for this entire input region, let's say the output should stay, maybe it should always predict as a cat, like a single classification level, right? So these are the kind of properties that the verifier will take. And again, just to overemphasize, not overemphasize, but re-emphasize the point that this is not only specific to adversarial examples. You can specify any kind of property, right? You can specify, any input region, any specific, any output that you desire, right? The catch, though, is the input regions have to be describable in a succinct form. Because you can imagine if the region is super weird, describing them, right, might require essentially too much space, right? Like, imagine it's some sort of arbitrary polytope, right? You will require a lot of half planes essentially to describe them, right? So that's kind of increases the complexity of the verification problem. But again, this is in scope, right? But most of the cases we are going to talk about will assume that your input region is much more nicer, right? When I say nicer, I mean maybe it's a ball, right? Maybe it's like a L2 ball, or maybe it's a hyper rectangle. Those sort of nicer, easier to describe regions, right? So that's basically the idea. And then once you have that, the goal of the verifier is to either tell that this property is satisfied for this region, right? That means the output stays the way it's supposed to stay, or it's supposed to give you a concrete counterexample demonstrating the violation of the property that you desire, right? And again, remember, a concrete counterexample must satisfy two things. It should violate the output, right? It should produce something that's not expected, and it should still stay within the region, right, of interest, right? Because that's the way we are defining it, right? Okay, so that's that. And a general form of these safety properties, a normalized form can be thought of as f greater than 0, right? So that's kind of thing. You can say, the output has to be greater than 0. And the main challenge in this business is that the neural network by design is a highly nonlinear function, right? And the nonlinearity makes it harder to track, right? Its behavior. So that's kind of the main challenge. And as we'll see here, and we're going to focus mostly on ReLU-based networks. The same principles apply for other cases too, other kind of non-linearities, but we're going to focus on the ReLU-based case here. So each ReLU, as I'm sure all of you know, it has two nonlinear pieces, right? So you can see it here, this piece and that piece, right? So these by themselves are not that bad. They're just like two nonlinear pieces. Problem is, in a real neural network, you will stack many railroads, right, together. And as you are stacking them, essentially the number of potential linear pieces in the final output, like the final composite function, right, can potentially have 2 raised to n linear pieces, right? N is the number of, ReLUs, right? Because each is contributing 2 pieces, right? And this is where the blow up comes from. This is what makes the problem, extremely challenging to reason about, right? The output. And again, I think intuitively, I guess it probably is, I mean, I won't say obvious, but like it probably makes sense, right? To think about if your input region is small, it's easier to reason about, right? Because, most of the ReLUs either stay on the active region, right? That means they're on or they're off, right? They don't flip, right? But as you make the input region larger, some ReLUs will turn from off to on as you move through the region. And, reasoning about them, their compositions, is kind of the main challenge, right, in this business. And again, it has been shown by prior work by Katz et al. That this is actually NP-hard, this particular problem of verifying, the output of neural networks. So ideally, you want to get what is called a complete verifier, right? So that means given any property, it should always prove or disprove, right? Given sufficient time, right? Given a neural network, given a property, right? Now, of course, as I said, this is theoretically NP-hard. Therefore, this is not very scalable, right? So in practice, what we'll always have is some timeouts, right? There will be some cases which are very hard, for which you'll run it up to a reasonable point, and then you're going to say, well, I can't say, okay, it can neither prove nor disprove this property. So that is unavoidable in this business. What one can hope for is to cut down those cases as much as possible, right? In some sense, you can think of it at a very high level. This is to like set solvers, right? Like, again, set solvers have made a lot of progress if you're familiar with the field, right? But still, there are a lot of hard cases for which the set solver is going to say, I don't know, I can't prove or disprove this. So that's the challenge. Now, of course, in practice, as I said, like many of the problems are not, I mean, NP-hard is kind of a worst case result, right? So in practice, there are easy problems too that can be, thankfully verified or disproved quite easily, right? I mean, of course, on one hand, right, there are these, neural networks which are completely undefended, right? You can just train them, like a regular training process without any robustness. And there, just running the attack will give you a counterexample, right? So if you just run, let's say PGD or whatever the state of the art attacks are, will give you a counterexample. So we are not talking about those cases because those are very easy to disprove. We are talking about cases where you have applied whatever robustness technique you want to train, and your interest, and you have run these attacks, right? And couldn't find anything. Then the question is, well, can you now guarantee that there are no violations, or or not, right? So in some sense, you can think of it as at the opposite end of the attack-driven testing, right? On one end, you can try attack-driven testing. If your network fails, those tests with very high rate, right? Let's say 90% attacks succeed, right? Then there's no point in even going to verification because why bother, right? It's clearly broken. But then on the other hand, imagine you run the test and like the test success rate is very low. Let's say like, the attack success rate, 1% or whatever. Now, the question is it because the attack is not sophisticated? There is some more sophisticated attack that the attacker can come up with, or there's literally no violation there, right? So that's where this verification angle can really be helpful, right? So that's kind of the basic idea. And in practice, as I said, like if you want to get a exact bound of the output of a neural network for a large region, it's going to be computationally very hard. But again, the good news is that in a lot of cases, you don't need a very tight bound as long as you can satisfy the property with a sound bound. Sound bound means it's always one-sided error. It will only over approximate, never under approximate. So if you can, verify a property with that sound bound, that's enough, You don't need to get the exact range of the output as such, right? An example will be, let's say if you're trying to prove a property f greater than 0, and let's say you get a sound bound, like between, let's say, 2 and 100, right? That's enough, right? Because you know that you don't go lower than 2, right? Even if the real range might just be, let's say, 2.5 to 3.5 or whatever, right? So that's that's one thing these sort of techniques exploit. All right. Okay. And so in practice, often the complete verifiers, are built using incomplete verifiers as a basic block. So you can think of it, incomplete verifiers are relatively cheap. It propagates a bunch of bounds through the neural networks. It's relatively efficient, but loose approximation. And again, loose means it's the error is one-sided, right? So it will always over approximate, but the over approximation error might be very large, right? And therefore, it tends to have many false positives, as you can imagine, right? Because it's over approximating. But the good part is that the soundness of the verification is guaranteed. That means if whatever your estimates are, with that estimate, if the property is not violated, it's not going to get violated, right? So you can verify. But there will be a lot of cases for which it will look like the property is getting violated, but it's not truly getting violated. It's just an artifact of the over approximation error of the process. All right. So branch and bound. Now, if you take a step back and think about how to build efficient complete verifiers using this building block of incomplete verifier, branch and bound is a framework for doing that. So essentially, what you are going to do is branch and bound has two steps. One is branching, the other is bounding. So you start with a given input region. In this case, we call it robustness region and the safety property. And then what you do is you keep on branching into subproblems, all right, and try to verify each subproblems. Now, subproblems, can be defined in many different ways. The simplest way is just splitting of the input region, right? As I said, if the input regions are large, getting tighter bounds are harder. But as you make them smaller, the over approximation error goes down. And of course, at what rate it goes down, that's a different question, right? But it is guaranteed not to increase, right? So that's one of the properties of the incomplete but sound verifiers. So keep on doing this. And then as you are able to verify certain subproblem, you stop there. You don't branch there anymore, right? And you are using incomplete verifiers to verify each of these subproblems, right? So let's say you can't, for C2, let's say your incomplete verifier couldn't verify it, but you couldn't find any concrete counterexample either, right? So then you need to split C2 even further, right? So you'll keep on doing this until, you kind of either you're able to verify the entirety of the subtree, right? Or you time. Okay, so that's the basic idea behind branch and bound. And again, some of the early works were done by, again, our group, and there are some other groups too. But this has become a very popular, and I think by now the most popular, framework for doing neural network verification. Pretty much all the state-of-the-art tools use this this formulation, this framework, right? Okay, so now let's kind of take a slight detour into how to build this branch and bound based verifiers, right? So I showed you the very high level idea of how to take a fast incomplete verifier and build these complete verifiers, right? By splitting these regions. But then the question is, how do I even build a fast incomplete verifier to begin with, right? Because remember, the goal is to have one-sided error. And it's not quite obvious how to do this, okay? So this is where we are going to take a look at. This is one of the prior works by called Crown by Zhang et al. This is from NeurIPS 2018. This is not our group's work. This is from UCLA. We are summarizing it because we build upon it. So essentially what this sort of incomplete verifiers do is they make bound propagation through each layer of the neural network, right? So you have this neural network, you have this ReLUs, and as you go through each layer, you are trying to get an upper bound and a lower bound for each ReLU, and then kind of compose it as you go all the way, right? And this should give you an upper bound and a lower bound on the final input, right? As functions of the original input, right? The features. So that's what you are trying to do. And of course, as you can imagine, right, getting this upper and lower bound is itself is tricky because of the nonlinearity of the ReLU. Right? So the basic idea, as you can see here on my screen, so this is a ReLU, let's say. For each ReLU, you have an idea, an estimate of the lower bound of the input and the upper bound of the input. So in this case, this is L and U, right? And then you have this, and of course, if L and U are such that the ReLU is, either on the on regime or on the off regime, then it's easy, right? Because then it's linear. Then there's no error in estimation of the output in that case, right? But the more interesting case is where it flips between, like, basically, part of the input it can stay off, part of the input can stay on, right? And this is what is happening here. As you can see, L here is on the 0 side, right? I mean, where the ReLU stays off, and then U causes the ReLU to go up, right? Like to go on. So then, given this, the upper, as you can see here, the orange triangles, right? So the outer lines of these triangles are the upper and lower bound, right? So this is an upper bound slope. If you can see my cursor, and this is the lower bound slope, and the same thing here. Okay. So now one thing to note here is that you might be thinking, wait, why not just take the convex hull, right? I mean, why not just take the line connecting the L and U of the ReLU, right? And that will give you the tightest linear upper bound, right? Which is true. But then you have to ask this question: the tightest linear upper bound for what? For that individual ReLU. Yes, it's the tightest, right? But often what happens though is, remember, what is your interest? You are trying to get the tightest bound on the final output, right? And you don't know which intermediate ReLU causes how much to the final output, right? So in certain cases, certain ReLUs matter much more. So therefore, you want to get, the tightest bound possible there, and at the cost of allowing more error in the other ReLUs, right? So essentially, you want to find a relaxation over all of these ReLUs that will give you the tightest bound on the final output, right? And that is a non-trivial problem. That is a global problem. So just because you are doing the tightest possible relaxation, linear relaxation for each ReLU doesn't mean you are going to get the tightest possible relaxation in the final output, right? So that's what the issue is. In this particular case, Crown did two different kind of relaxation. One, and they had this parameter called alpha, which was for alpha equal to 1, they picked this particular type of relaxation, and alpha equal to 0, they did this kind of relaxation. As you can see here, they both have errors, right? Both of these relaxations have errors, but they have different kind of errors, right? The erroneous regions are different. As you can see, like, this orange triangle has more area, right, than what could have been output by the ReLU, right? So those are the error regions. So in this case, because can everybody see my cursor? Like, or should I use like a laser pointer or something?
No, I can see your cursor.
Okay. So this region here, see, this is the error in this case, and this region here is again error, right? So it's just that they have errors in different places, right? So what they did as part of this work, Crown, this was one of the early works, they basically said, well, we'll use some heuristic to control which value of alpha to use, right? And we're going to use that to kind of keep on doing bound propagation. Okay, so that's the basic idea. And this is an example here, right? So for example, if the ReLU takes like this particular input here, it's a simple neural network, this is what the upper bound is going to look like, this particular format of the linear thing. And as you can see here, X and Y are two inputs here. This is a very simplified case where there are just two features, okay? X and Y, two inputs. So this is what the upper bound is going to look like for this particular case where alpha is equal to 1. Okay? And if you pick alpha equal to 0, obviously it's going to be different, right? So this is this, and this gives you much tighter bounds than what the basic tools were there, right? There are other tools there, and then the goal was to try to kind of get the tightest bound possible, essentially get the output to be as tight as possible over this XYs, right? So this was this prior work. So that was great, but then we kind of tried to build on it. The question was, well, how can we improve? So of course, one obvious question to ask is, should alpha always be 0 and 1? Can there be other values? Right? Is there value, like, can the tightest bounds in the output can come from other values than 0 and 1, right? And the result, is actually yes, right? Basically there are cases, you can construct cases where, the value of alpha, between 0 and 1, some specific value will give you tighter bounds. That depends on, what the weights are, right? How much the ReLUs are contributing to the final output. Right. And again, from here, as you can imagine, the obvious next step was, well, why not treat alpha as parameter, right? And why not optimize alpha, right? And again, when I say optimize alpha, essentially what I mean is for each ReLU, you introduce one parameter, extra parameter, right? Alpha, right? And your goal is to find the values of alpha that will give you the tightest output range, right? Because clearly the tighter the output range, the better for us, right? For the verification purposes. So that's what alpha crown is. And essentially we introduce this optimizable parameters called alpha. Now each ReLU has an associated alpha with it, and we're going to use, of course, gradient ascent or descent to jointly optimize, right? And optimize, the idea is, as I said, find the best values of alpha that will give you the tightest output range, right?
Just a quick question, Suman.
Yes, yes.
So when you say optimize, is it like the loss function is written in a way that the bound should be tightest at the output, and the gradient descent takes care of optimizing alpha for every ReLU appropriately by itself.
That's
the loss function is just that output.
That's right. The loss function. So to be more precise, I didn't mention that, because remember I mentioned that we are getting the linear approximations of the output, right? So what we do is we put concrete values of the input ranges, and then we will get an output range, right? Let's say, let's say the output for alpha equal to whatever. Like, let's say there are like only one ReLU, just to keep it simple, right? So let's say if I set alpha there 0.1, right? Let's say I get output range 1 to 100, right? So the width will be 99, right? 100 minus 1, right? So we have a notion of, the width of the output, right? And then that's your loss function. You just want to minimize it, right?
Got it.
And the reason this works, remember, is that the way we have picked alpha, whatever value of alpha we pick, the relaxation is always sound. That means it's not gonna under approximate the output, right? It's just that it's gonna over approximate it with different kind of errors, right? Therefore, whatever value of alpha the gradient descent optimizer picks, the output is still sound. We're just trying to find the cut down the over approximation error, essentially.
Yeah, makes sense. It has to be tightest, but yeah, the soundness is pretty good.
That's right. Yeah. So that's the basic idea. Thank you. So now that you do this, you can kind of now we see here again just an example of the tightness. And again, when I say tightness, I'm literally talking about the width of the output, right? So this is an example here. In this particular case, the ground truth is 0. So this is not the width. This is the actual, like the output. It's like it could have been 0, like the minimal value. I'm just talking about the lower bound here. And all the other techniques, as you can see here, they're kind of, like a little bit. There is quite a bit of an error, like 0 minus 3 minus 1.5. As you can see, alpha crown improves this, to kind of smaller, right? Make the error smaller, essentially, than the prior work, right? So that's kind of the main advantage. And as you can see here, compared to crown, there is a little bit of a time overhead, right? It's like 0.2 second compared to 0.1 second. And that's because, remember, crown used very cheap heuristics to decide for each ReLU, what value of alpha to use. But now we're using propagation, right? We have to back prop and then do forward prop, do a few iterations. So that's where the overhead is coming from. But again, once you start using GPUs, this overhead scales very well, as we all know, with the number of alphas, right? So that's kind of the other benefit too, right? That this back propagation can be done very efficiently by using standard GPUs and the corresponding libraries. All right. So that's that. And again, just to compare this with some of the prior work before this, the main way people tried to do solve this problem, this relaxation, is before this work, before Alpha Crown, was essentially to use this tightest possible relaxation, right, which is this convex hull essentially, and then use a linear solver to kind of get these bounds, right? So you can kind of call the linear solver, just convert this whole thing into a linear program, and then just call the linear solvers, right? So that has been how people have been using it. But also we're using mixed integer programming solvers in this context. The main problem is that this conversion process and calling to the LP solver is quite heavyweight, right? And often LP solvers cannot exploit GPUs as well as the gradient descent-based techniques and other techniques. So that's like one of the major bottlenecks of those work, right? So in Alpha Crown, if we have fixed intermediate bounds, that means if we fix values of alpha, right, we'll still get the same tightness as LP verifier. But the performance is much better. And of course, if you jointly optimize the alphas, right, you're going to get better values than the standard LP verifier. And again, just to be clear, you can use LPs like linear programs, right, to solve this problem too. This is also possible. It's just that at that point, the way LP verifiers were being done, they're not being done for the optimizing the joint problem. They're just being used to solve this, the fixed relaxations, right? So that's why our bounds were tighter. But again, the main advantage of our approach is this efficient use of GPUs, right? That cannot be done with the LP-based techniques. So that's that. So I talked about the good parts of Alpha Crown, but there are two main limitations that I would now like to talk about. One is that it often in this process, as you are doing this, incomplete verifiers. Now, if you take a step back, think about my initial picture. Remember, we have to do many branch and bound cases, right, over these incomplete verifiers. And when you are branching, you are creating sub-problems. That means you are adding more constraints, right? As part of those splitting, right, there are two kinds of splitting. One is input region splitting, which is fine because, you should be able to split input regions into like a bigger hyperrectangle, into smaller hyperrectangles. That doesn't present, that much challenge. But in a lot of cases, the number of input features are too many. Okay, so if you split there, the potential width of the tree is very, very large. So what you instead want to do is, instead of splitting there, in a lot of neural network, the architecture is like a funnel, right? So you kind of take a large number of features, narrow it down to an intermediate layer, and then you do something. So you ideally want to split in the intermediate layers, right? And that means you need to add additional constraints about those ReLUs, right? You're basically saying, look, intermediate layer now, this ReLU should always stay on. Under this condition, is there a violation, right? So that's like an example of a sub-problem. So those kind of constraints, is very hard. Basically, the standard technique that I showed you with alpha cannot handle those kind of cases. LP solver can handle those kind of cases much better because remember, each ReLU has two linear cases, right? So once you split, it's just a linear problem, right? It's just a linear constraint. And of course, LP solvers are designed for that, right? So they can get far tighter bounds there. On the other hand, our bounds will be looser, right? So that's kind of one of the issue in terms of using it as part of this branch and bound thing. But of course, as I said, on the other hand, we are much faster on GPUs. So we can explore many more sub-problems at the same time, and that's what we do. And then the other issue is that as you are adding this more and more constraints by by branching, at some point, many parts of the tree will become infeasible. That means those values are not possible, right? Like those, like some ReLUs, let's say in some input region will always stay on, right? So if you try to set it to off or something else, that's infeasible, right? Detecting that is key for performance, because think about it. If you can detect them early, you can stop the exploration of the node right there. So you can kind of back up quickly. The earlier you back up, the better it is, right? So that kind of stuff again is hard to do, because detecting infeasible problems the way you did it is hard, because gradient descent cannot give you any guarantees about the other side, right? It can basically get stuck in local optimas, and you cannot make a statement about the other side with guarantee. So essentially, completeness cannot be guaranteed by alpha crown alone, right? So what we do, as you can imagine, is basically we just fall back to the LP solver for these cases, right? We basically say, look, as soon as you start splitting this intermediate neurons, right, we'll use linear solvers, but we'll just try to minimize use of it, right? Similarly, if we have some cheap heuristics to decide whether something can be infeasible or not, if it's likely to be infeasible, we'll call the LP solver, right? So at least that way you can kind of balance the both sides, right? You can get the GPU performance benefit as much as you can, still fall back to the LP solvers, when you can. Right? So that's the basic idea. We built Alpha Crown. It was around 20x faster than the native LP-based verifiers. And on the right-hand side, I'm showing these graphs. They're essentially different kind of benchmarks. And when I say base easy, base medium, they're different kind of neural networks. They're referring to different kind of architecture of the neural network, right? Like how many layers are there, are they wide or deep? And then, here, this method list is essentially a different kind of existing verifiers. They're showing the numbers. So, so again, the overall trend, though, is that we were quite a bit more efficient than others. So that's kind of the basic idea. So we used in the next version of the tool that's called Beta Crown, we actually solved both of these problems using a dual formulation of the LP. I'm going to talk about it in a second, let's first take a bit of a closer look of what the issue is, right? What these two issues are before I go to Beta Crown. I would call it alpha beta crown. But essentially, the main challenge, as I said, is you want to be able to support linear constraints resulting from splitting of ReLUs. And when I say splitting, I mean, you want to do case-wise reasoning, right? Like you have essentially, you start with one subproblem, you split it into two subproblems. In one subproblem, this ReLU is always on. In the other subproblem, this ReLU is always off, right? And that will result in constraints, right? So that's the problem we are talking about, right? So here is like a simple example of the kind of constraints that result from splitting of the ReLU. So here, as you can see, it's x plus 2y equal to greater than 0. This is the constraint, and of course, linear solvers can deal with this very easily. But we don't want to go to the linear solver because of the overhead involved going there and the lack of parallelization, right? Lack of use of GPUs. So the question is, well, how to get rid of it, right? Can we do something, right? So this is where we use the dual form of the LP. Essentially, again, if you're familiar with the duality of LPs, right? So each LP has a dual form, and the Lagrangian dual is what I'm referring to. Essentially, these kind of constraints can be incorporated. I mean, this constraint problem can be converted into an unconstrained problem, right? By introducing another parameter called beta, right? And this is the format, right? This is the new objective, right? And you want beta to be greater than or equal to 0. And then the question is, you want to find the best value of beta, right? That's possible, right? So that's the standard formulation, and this will allow us again to use gradient descent, right? So that's kind of the main advantage of using such a technique, right? And yeah, as you can see here, if we get the right value of beta, we'll get to the same tight results, right, that LP solver can give, but we can still use the gradient descent powers, right? Right. So that's that. And of course, the good thing is any beta essentially will produce a sound lower bound, right? Obviously, in most cases, we do find the best value of beta because this is a convex problem. But even if for due to other kind of computational errors, round off errors and whatnot, even if you don't get to the best bound, it's still guaranteed to be sound. So that's another great advantage of this approach. And then, so the only side effect though is now we have introduced more parameters, right? Beta is another parameter, right? Now you want to jointly optimize both alpha, beta, right? As part of this whole process. And the other thing to note is that the other subproblem, if you remember, the other issue with alpha crown was that you cannot solve, you cannot detect infeasible problems, right? So that was another issue, and that also gets solved here because essentially there is this very well-known result in Lagrangian duality that if the dual is unbounded, then the primal problem is infeasible. Right, so we exploit that property. Basically, unbounded dual means the objective is going to go to infinity for the base value of the objective is essentially going to go to infinity, and therefore we can say this is infeasible, right? The primal is infeasible. The primal, as in the original constrained LP problem, right? So that kind of allows us to solve both of these issues essentially to kind of jointly optimize. And this is kind of the more general formulation. I think I will probably just skip the details because I think for the interest of time we're almost on time. So let me kind of just remind you that these are the two main techniques. Basically, the dual formulation allows us to do this. And let me just skip over the entire thing. Sorry. And just one thing to show though is, as you can see here, like which LP solver, the tightness is exactly same, let's say in this case with our beta crown, but look at the gain, right? So it's 10 seconds as opposed to like 0.304 second, right? This is like 0.4 millisecond. So so that's a massive gain, right? So that gain comes from the usage of GPU, the infrastructure that has been developed by the machine learning community to do efficient training of neural networks, right? So that's that. And overall, we use this again against a bunch of different tools. There's fairly large, significant kind of gain. And more importantly, there is a competition. Let me kind of skip over this. Yes. So there is a competition of pretty much all the state-of-the-art tools that participate as part of CAV, the Computer Verification Conference. They have been running it for the last 3 years now. There is around 10 or 15, I think last year it was like around 15 or 18 verified teams that participated. They had a set of benchmark designed by others. We won it back to back. We won 2021 one as well as this year's 2022 with the same tool. And again, so that, again, that hopefully kind of shows the promise of this approach. So that's with that said, I think that's it. It's kind of I guess for the interest of time, let me stop here and take any questions that you may have. Thank you again.
Thanks so much for the amazing talk. To make it convenient, I think everyone can unmute themselves now. So I removed that restriction.
Oh, I think there's some questions here. Sorry. Yeah, maybe. Katerina, do you want to kind of, oh, sorry, I can actually read it. So, okay, all right, yeah, so I got the first question, but I think you said 2 questions, so maybe you're typing the second one? Oh, yes, you are typing the second one. All right, good. So let me read through the first question. First question is, how does alpha crown generalize to other activation functions like 10H? That's a great question. At this point, we do not support 10H, but there are other work trying to support, other activation like 10H. In practice, 10H is a continuous nonlinearity, right? So in practice, what that will boil down to is you have to do piecewise linear approximation of that nonlinearity, right? And then kind of try to reason about that. So in some sense, so far in each ReLU, I said there are 2 nonlinear pieces, right? For things like 10H, there are going to be, a lot of nonlinear pieces, right? But which nonlinear pieces will be active at which time depends on the output, depends on the input range of, those 10H, right? So it I mean, I guess the very high level answer is it can be generalized. It will require more computation than that. And because ReLU-based networks are, kind of quite popular, right? Most of the effort in the community has so far gone into ReLUs, but I think there's no fundamental reason, at least at a very high level, to not support the other ones. And the second question, I think, is you said, how can we use constraint splits in practice? Are they merely used for split its constant, or should we have some sort of domain knowledge? For example, some deeper neural networks can be very difficult to interpret. What would be the interpretation of having this ReLUs in the middle of the network that should always stay on? Why should you want to verify that? Right. So let me take, so that's also a great question. So let's take a step back and kind of ask why these splittings are needed. The way I was talking about the splittings, remember, has nothing to do with the property, right? So the property is end-to-end, right? A safety property, you just say, look, given this input region on the feature, right, features, you want this output to satisfy, whatever, like it should always stay this class. Now, you don't care at all about input regions, right? Sorry, you don't care at all about the intermediate ReLU outputs, right? So the splitting is merely a technique for the verifier to make its reasoning easier. Okay, so you don't care about the fact that the ReLU should always stay on or whatever. The verifier cares about it because it will make its life easier. Okay, so that's why this splitting, this branch and bound, is completely invisible, right, to the end user, right? So that's the way I was talking about. Now, of course, you can always ask this question, right? Can this sort of information, let's say the verifier finds it, okay, that it's mostly, this ReLU stays on or whatever. Now, can this additional information be useful, right, in terms of interpretability of the network, right? That's a great point. I don't know. I mean, so far we have not tried to do that. But again, I can imagine saying, hey, look, this ReLUs, the nonlinearity is not being used at all for this thing. And again, if you do this many times, and then this happens to be the case, that might be a good candidate for pruning, right? I mean, Vikash has done several great works on kind of cutting the size of the neural network. I'm sure there are overall the community has done a lot of work there. So those kind of stuff can potentially be useful, right? Information for that guidance, but we have not tried that yet. So at this point, the splitting of the neural network is merely a technique for the verifier to make its reasoning easier, right? So it's not even exposed to the to the user of the verifier, or it's not even mentioned in the property that you want to verify, right? And again, if it doesn't answer your questions, please please feel free to speak up or ask more.
Yeah, thank you. It addressed all of the questions. Thank you.
Thank you.
Is there any other question? There's something like a bit on the high end, Suman, and this is something I think you must get a lot, and it's about like scale.
Right.
So it's like, when would we see these verification methods on ImageNet, and to really make it fine grained, I want what's the bottleneck if we see some of these techniques being like scaled to
Right.
say a ResNet 50,
Right.
and even more precisely, that it's like more of like with your GPU based techniques,
Right.
the like we can actually leverage computation, so that box is checked.
Yep.
It's I think if I remember looking at the code base, it's also to a good extent it's a standard machine learning paradigm, like write a loss, let SZD take care of the optimization, and sort of like the bounds are can be optimized like in this like a simple SZD fashion. So a good amount of boxes are already checked.
Right.
So like what's stopping, or like what is it that the community is like sort of like running into that doesn't let it scale up to ImageNet, even after a good amount of effort and groups have sort of like invested resources into it?
Right. So yeah, no, that's a great question, Vikas. Thank you. So I think two things, right? One is I feel like verification in some sense, gives you the strongest possible guarantee, right? In the sense, it basically says that, look, within that input region, right, no matter what point you pick, right, the output is not going to violate this, right? So in some sense, I think verification is always a bit of a catch-up game. In a sense, if you look at traditional software, right? Even there, right, verifying the largest pieces of software has always been a challenge, right? So, and as the verification technique kind of scales, the software itself scales faster. Like, the average size of, let's say, Microsoft Windows, used to be whatever, right? X GB, right? Now it's like the distribution is like whatever, right? Like distribution as in the size of the binaries and all the, paraphernalia, right? Is like, maybe 100x or like 50x. Right. So I feel like there is that aspect of it too. And I think the other issue is in a lot of cases, right? If you just take a regular neural network and try to verify it, sometimes it's very hard to verify. So I think in my mind, there are kind of two major ways of making progress. If you really want to scale up to image net or like something state of the art, essentially, right? Like transformer for that matter, right? I feel like one is you can try to weaken the guarantee a little bit, right? Instead of just saying, look, because you have two extremes, right? You have like verification, which is like very strong guarantee, but doesn't scale quite as well. On the other hand, you have these attacks, which reasonably scales well, like you can run them on pretty much any large network, but then there's no guarantee whatsoever, right? You're like, you run it, and if it finds things, great. If it doesn't find things, what does it mean? Hard to tell, right? So in my mind, it will be interesting to kind of think of, weakened guarantees, mostly probabilistic guarantees, but at least more meaningful, some meaningful guarantees, which will kind of trade off computation with strong, like strength of the guarantee, right? And at the very limit, you will have, verification, of course, right? So I think that's like one, potential. And again, there have been some work in the community going that direction, but I think there is a lot of room there for like exchange of information in that format where it's like, look, this region I can easily verify, great, right? This region I kind of cannot verify, but maybe I can say something meaningful about it, even though I can't verify, right? So I think there is a lot of scope potentially to go with this bounding techniques together with smarter sampling techniques. Right now, the attacks use some kind of random samples and run them as starting points, like treat them as starting points for PGD or whatever that, right? But like if you have a better idea of the shape of the function, right? Even if it's like crude over approximation, your sampling now can potentially be guided by that, right? And exploit that fact, right? That here's like what I have figured out. So I feel like, again, I've seen some work along those lines, but like that is much underexplored, I feel, which can potentially be very promising. That's like one direction. The other direction, I'm sure you're well aware of, is trying to train these neural networks, right? To jointly minimize the training loss as well as make them, easy to verify, right? Essentially, keeping the estimation tight, right? So basically, you run the verifier, part of the verifier, as part of the training process, right? And you say, look, I want both. I want the weights to be picked such that the loss is low, regular loss, and it's easily verifiable. So that made quite a bit of progress initially, right? But then it turned out, again, as I'm sure you know, that these two losses are conflicting. These two goals are conflicting. So now it's very hard to train a network that will, achieve a good regular loss while still be verifiable. So the moment you make it easier to verify, now the loss is high, right? Then that network is not of much use, right? On the other hand, if you get the loss low, it's harder to verify. I don't know at this point. I don't think there is any kind of, as far as I know, there is any breakthroughs in that direction. But I think that's also another fundamental thing to understand. Is this conflict fundamental? Or because it's one way to kind of pose it is some sort of conflict between capacity of the neural network, right? Versus, basically, if you make the neural network mostly linear, right, over large regions, clearly it's easy to verify, right? It's much easier to verify, but then it may not have enough capacity to adjust the decision boundary, right? So it's not clear if it's a fundamental conflict. I mean, this verifiable loss versus regular loss, or it's just an artifact of the current verification tools. But I feel like these two are the main things. And you're right, like, scaling up to state of the art is really is an open challenge. Like we're not there, we're nowhere there.
I guess then a natural follow-up question would be is, is do we have a good understanding in the community of about the scaling law? Is like if I remember correctly from like early first year class in on set solvers, is that if we take the complexity of problems like number of predicates, I guess, and there's like an inflection point or something
That's right.
that
That's right.
after a while it becomes really hard suddenly.
Yep.
Why? Maybe I don't know, like maybe there's answer for that. So if we just like do we know if we plot this number of parameters, number of layers, or some sort of notion of capacity or scale versus the time it takes for the solver? Like, like is that something that's that the community has explored, or like what's your take on it? Like, what's the scaling
Right.
law here?
Right. So I think at this point, I think it's still scaling, reasonably well, if you look at, because this is a relatively new field in terms of overall community, right? But I think I don't think there is very clear understanding, as clear an understanding as the SAT case, because SAT has been there, like the SAT solver have been making progress for like, a long time, right? Like 10 years or so, like even longer than that. So I don't think at this point, we have a very clear understanding about like where it becomes hard. But I think it's a bit more complicated in this case than just the number of the clauses, right? Because in here there can be a lot of inactive ReLUs, right? So just because the size of the network becomes larger doesn't necessarily mean that the properties get harder. And also it depends on the property itself. Some properties are very easy to check, right? Because imagine you are only interested in narrow regions, right? No matter how big the network is, right? So I think there is a bit of an issue there. And I think the main challenge, or the main the understanding angle, is what is the limit in terms of like, limit as in not theoretical limit, but like just like in terms of gains, right? In terms of like, if you think of the yield curve, right, is like what is the biggest chunk of the network, right? Like what is the biggest sub network in some sense, right, that you can reason about efficiently, and what properties that sub network should have, right, to make it efficiently reasonable. And then if you have some understanding of that nature, that can be a good way of breaking the branch and bound, right? Because if you know that you can't reason about something bigger, right, you might as well just throw it to the parallel GPUs and try to make as much progress as you can. So I think that is still an open problem, right? I mean, ReLU splitting, I was giving you as an example, is just a simple way of doing it. It's not very good, right? Because why split one ReLU? Why not split like 5 ReLUs? Like you can kind of always make this, like basically you can always identify a subnetwork and say, look, everything in the border stays fixed, right? Like all of them kind of, either stay on or either stay off, right? So it's not quite clear. I think you don't definitely have like the SAT level of clarity, like SAT solver level of clarity, partly because I think it's a much more evolving new field, and also partly because SAT solvers, they're dealing with discrete stuff. Here, things are continuous values. The effect is not just there is an effect or not. Like it's like, well, it may have very high effect in certain regime, like certain region, and then suddenly have low effect, right? So, and again, that being said, I think it should, definitely should be done, but we're not there yet.
I see. Yeah, thanks a lot for clarifying that. If is there any other question? Otherwise, I think we are right on time. And last thanks our speaker again for the wonderful talk. And yeah, thanks Suman.
Thanks, Vikash. Thanks everyone. Thanks for attending.
See everyone next week. I think next week is a scheduled break, but see you after that.
All right, sounds good.
Bye.
Thank you.